Okay. So far now, whatever we have discussed, let us briefly summarize such that we should be in the momentum. So let me quickly start. So today we are discussing about the role of machine learning and deep learning in how we can improve this in the geophysical subsurface imaging. So our main idea of that is very simple. How we are going to utilize these advanced interpretation algorithms to improve our subsurface imaging. Now the question is that how we can improve it, and the moment what is the need to improve, because the moment you will improve the subsurface imaging, uh, your chances to identify whatever the natural resources you are targeting is getting better and better. This is the main motive of this work. We divided our problem in 7-step framework to utilize that one, and we discusses that a major thing, most of the interpretation parts come from modeling from data to getting the subsurface model. We call this as a numerical optimization, geophysical inversion, geophysical inverse theory. These are the problems we discusses about the what is the in our research group what we are doing currently, and how we can better way to model your subsurface structures. There are different flavors for that. We discuss this one, and then what is the role of advanced uh, unstructured grid-based discretization, because it can take care of the topography and irregular shape you can also incorporate. So these things we discussed, and some of the terminology we discussed, that how we to perform any kind of optimization, what is the how we can keep our data points, how we can keep our model points. These are some of the couple of things we discussed, and then what should be our minimization approaches. And we discussed that this kind of a minimization approaches will not be have a sufficient to obtain all kind of a model over here. So we defined our problem statements related with the uh, consequence of the inversion algorithm. Also, we problem statement with the identification of geologic scale, which was a relative scale because of the geological boundaries were not too much clear. So we went on the first basket to improve our subsurface imaging, which one was the machine learning based algorithm, and then we did fuzzy Siemens clustering and kernel density estimation based algorithm. And in that, how what was the mathematical framework by which we can combine it. And these are the mathematical framework where the way how can combine your uh, minimization function with the machine learning to improve the images. And then further we came up with another approach, which was the deep learning. So what is the effective way to train your geological model such that you can generate different combination of subsurface uh, model parameter. Now we discusses the different architecture which we are going to compare. So one architecture was unit architecture. There are many literature already available of that one, but geophysics point of view there was nothing. Then we tried also attention unit architecture by following the work of Oktay et al. 2018. This is a very classical framework which we defined. And then we here we our in our lab we develop this kind of architecture we call variational encoder decoder network. This network was already developed for not for the image classification for electrical engineering department, but uh, for geophysical problems it was not there. So our current PhD student who are working in this one, so he modified that one and he got the rough idea about how to do that. Then who are in the world who are going to utilizing this kind of a concept to improve the subsurface imaging. Mainly two groups are there: Ward et al., who is in the British Geological Survey, who is doing that one, and Dorsey in ETS. Now I think he is the Colorado School of Mines. I'm not pretty sure. I think he is in ETH. So these groups are working in these framework to improve that one. And then we started we came back to our inversion results. We compare the traditional inversion result with how we can improve it with our using the machine learning. So we noted that the here boundary were not too much clear, but by utilizing the machine learning, the boundaries became much more clear. Uh, to this point, we have discussed. Now let us see more and more results for that one. As I mentioned to you that the data misfit, if you compare the RMS error between machine learning, this L1 norm meaning is that L1 norm based minimization, and L1 norm FCRT meaning is that machine learning based L1 norm minimization. So you'll see that they are starting with the same homogeneous model, but in the initial phase they are taking the different path, but at the after 6 iteration both are converging to the same error level, which is quite okay, which is actually 1%. Now, second problem statement which I wanted to discuss, that this result whatever you have got is the interpretation of one geophysical data set. So one geophysical data set meaning is that you are trying to play with the DC resistivity data, then you will get one particular data set. Now, if you utilize the same area, you utilize the gravity data, then your result will be different. So which model you are going to trust? The gravity data, whatever the model which is coming from the gravity data, or the model which is coming from the DC resistivity data, or the model which is coming from the some other data sets. So which model you are going to trust? These are some of the fundamental questions was came in our model. So we were stuck with the problem that single geophysical data set will not be the sufficient to get complete subsurface information. So what is the solution of that? So the one obvious solution is that you take multiple geophysical data set over the same study region and try to obtain one conclusive model which will be satisfying all the geophysical data set. So by doing this, whatever the advantage of that, drawback of one particular method will be overcome by other geophysical method. So this is the main logic, main idea to apply that one. So now we can optimize using the joint module, joint framework. But if you apply this joint framework plus machine learning, then what will be the advantage of this one? We are going to discuss over this one. Now, the same framework we wanted to that. So goal is very clear. We wanted to enhance our resistivity imaging with other geophysical data set, for example, gravity data set. Now, in that kind of a minimization function, what should be our minimization function we should utilize? So for example, this is the DC resistivity minimization function, which is consistent of two terms. Now, second is gravity minimization function, which is also consistent with the two terms. But problem is that this model will provide another model, this gravity model will provide another model. So how we can couple these two models such that both should follow one particular agreement and their model should be unique? So we optimized, we added one additional term. We call this as a phi coupled DC gravity terms, which will actually job will be, it will try to make the relation between this M1 and M2. M1 is actually your model parameter for the gravity, and M2 is actually the model parameter for magnet. M1 is the model parameter for magnet gravity, DC resistivity, and M2 is the model parameter for magnetic data. So you can utilize these two concepts together. Now, what kind of a relation will be between these two? Because it will highly dependent on a different geologic scenario will give you the different relation between gravity and density. For example, if you wanted to choose one study area, it will provide you one relation, and if you are choosing another area, it will provide you another relation. But that relation is not clear with us, that what is the relation between density and resistivity of the subsurface. We do not have any idea. So in that context, we utilized again the supervised clustering based optimization framework to just make the similar model. So our logic was here to obtain a similar model and how we can improve the image. So in this category, there are two more. If you consider worldwide research, there are two major groups who is working, are actually following the two pathway to compute the relation between these two. One group is following the cross gradient based, meaning is that they will compute the cross gradient between these two physical property, and they will try cross gradient, and you create with the zero, then you will get the structural discontinuity pattern of that one. Second is petrophysical based. Petrophysical meaning is that you have an x-axis here, you have a y-axis over here. You put on the x-axis density value, you put on the y-axis resistivity value, and then you cross plot all the model and let machine learning plays with that and decide which parameter and what are the relation we are going to make. So we utilize this particular concept to improve our model. So let us see our result on one particular synthetic example, how our algorithm is working, and then once algorithm work, then how uh, we can utilize this one to improve the subsurface. So to test purposes, we have taken a homogeneous model as a host rock. We name this as a geologic unit 1. Geologic unit 1 has a physical characteristic of 100 ohm meter resistivity value, and density contrast is 0. 0 meaning is that this is the baseline of that. Now, second is our target rock. This is our one target rock 1. This is the target rock 2. Target rock 1 has a physical property value of 10 ohm meter and density contrast 0.3. And the target rock 2 also 0.1. One important point you note down that these two physical property, though it is has a target rock 1 and target rock 2, however, this has a different resistivity value, but we have considered the same density value. Now this one has the block which we are wanted to consider. So homogeneous background is actually 100 ohm meter, this 10 ohm meter resistivity, this one is the I think 500 ohm meter. So this is 500 ohm meter resistivity. Here we have a 10 ohm homogeneous background, and then we have a 0.3 density contrast value. Now this is the result of a traditional inversion. When you invert the DC resistivity data set, this one, you will get this model. When you will invert the gravity data, you will get this particular model. Now still this is confusing, and you will not sure that where is the boundary. For example, where you will draw the boundary between geologic unit over this. So still it is not clear. Then what we did, we utilized this framework. This whole framework, we put beta is equal to 1 over that, and we play with that. Machine learning should play the relation between that one. But here assumption was that each geologic unit is having a different uh, cluster value, different physical property value. So we utilize this one to improve the imaging of this one. So this one we obtain the relation between the using the machine learning. Now, one of the important point you should note that this is very close to your whatever the theoretical model. So model has got very drastic change when you utilize the joint inversion with the machine learning based results. Now here we furthermore refine that. We further assume that if you talk about this one, this depth is further quite going more and more. So further we put another constraint on that. This value, whatever the petrophysical value is, are known to us a priori. So we again further perform the inversion, then further results got improved. So these are the two important things where we are inputting this value. In the one thing, we have just assumed that this number of cluster we know to us. In the second case, this VI value is also known to us. So these two parameters we played. So our results got totally incorrect. So this is the result on a synthetic model. Let us go to the field data set where we are going to use. Now, before going to the field data set, I wanted to show you that this red block you are seeing over here is that this is 0.3, this is 0.3, this is the 0, and this is the 1 ohm meter, this is the 500 ohm meter, and this is the 100 ohm meter. Now, black color you are seeing all the cluster center value which you are plotting over there. You can see that it is scattered all over the places. But if you see the machine learning results, which is blue color or green color, you can see that they are very confined in a one particular place. To be more precise, this is the one machine learning value you are get when you assume that a priori this physical property value, when you assume known to you, then this greenish color is coming more closer towards the answer. And this is the result we got. one which was very encouraging. We reported in one journal also this result. Now, with this encouragement, we are going to utilize uh, the use of uh, this architecture in the improvement of this one on the field data set. Field data was belongs to very near to I think in IT Raipur. It is in the West Bengal district. We call South Purulia Seer Zone. I think Raipur will belong to somewhere here. Jamshedpur you can treat over here. At least it is very far away from IT Bombay, but very near to NIT Raipur. Now, this one is the one zone which we have wanted to survey, and how why this South Purulia Seer Zone I have marked, because this South Purulia Seer Zone and this Singhbhum Seer Zone is very important for mineral prospecting point of view, because there are many uranium deposits have been found. So our study area belong to the Beldi open cast mine, which is actually the source rock for uranium. Now, this is the geological map of the Beldi open cast mine. If you see that one, this is the open cast mine. So now if you go right now, that is filled with the water, but we wanted to study the extension of this uranium mineralization. Now, with geologic rock, we are getting the uranium. So there is a kaolinite rock. Kaolinite is nothing but clay parts. So this clay part, whatever you will get over the area, you will get the uranium bands which is occurring that one. And host rock is actually carbonatite plus ultramafic, or you can say ultramafic plus carbonatite is the host rock which is having this kaolin band into that. AMD is actively working in those regions, so they have provided us the borewell in BH1 and BH2. This one you can also get this borewell information from following the Katti et al. 2010 paper as well. Now we surveyed two geophysical data set along this profile, and one data set was the gravity data and another data set was the DC resistivity data set. We perform both individual result and the joint inversion. Joint inversion meaning, whenever I'm saying joint inversion, meaning is that I'm trying to compute with the help of machine learning. So this is the result of we got from the joint individual inversion of DC resistivity. This one is the individual result of the gravity, which is provided with the density model. Now, if you compare these two subsurface model, one thing is very clear that they are not matching very close to us. For example, this block is here going like that, but here you are seeing some kind of a vertical feature. And to be honest, geologically, these features are vertical. So gravity is quite here, it is providing more results, more good result. However, these features are related with the band which is responsible for kaolin, which is a low dense material. Density value is low and also very low resistivity value. So low resistivity and low density value we identify as a characteristic of uranium mineralization, which you got here. But only point was missing over these features are that we do not have any uh, structural similarity between these two models. For example, we do not have any feature belonging on this one. We do not have this feature over here. So there are structural discontinuity is already there. So we utilize the machine learning one to identify the similar feature of that one. So this result is the joint inversion result. Now you can see that how the result were very similar result we got. Structural pattern we got over here, one body we got over here. This is the vertical feature you are getting over with DC resistivity also. One vertical feature over here getting. Now you got this clear cut body over here which was not here. These two data set which this feature was here, at this point it is no feature, but here you can say that this is quite well fitting you are getting that. So these are some of the structural dissimilarity was there, but we computed that structural similarity for that. Now, we just plotted that what could be the possible relation between this resistivity and density. So machine learning if you red dot, whatever you are seeing is the result of individual inversion, single inversion. So there is a no particular relation, but this is the clustered relation which machine learning drawn to us. But one of the assumption, we assume that these cluster are actually circular cluster. Okay, one may assume the uh, ellipsoidal cluster. So in that scenario, we utilize here fuzzy image clustering. But if you wanted to use uh, this not circular cluster, then you, in that case, you have to utilize GK based clustering approaches, or even in that case, you have to again do the more and more advancement for that one. But here our assumption was that uh, circular cluster it is following, but we have got pretty good result. Now, important point is that if you compare the data fitting, is there anything we can say in the data? So individual level data and joint level data fitting RMS value was 1.6 point and 1.73, and here in the gravity data RMS value of 1.14 and here 1.110. So almost same level of data fitting we have also got. But if you compare your result with the borewell information, which was located over BH1 over here, BH2 over here, you will notice that these two borewell, these two geologic model is following the same pattern. For example, drilling direction of this borewell 2 was like that, same exactly having that one. So this is one geologic unit you got. This one is you got over here. So this is actually quartzite. This quartzite unit is over here. You got getting that one. One of the important parameter that here we mark this as a kaolinite rock, here quartz magnetite, apatite rock. These two are not differentiating. These two units are not differentiating. But if you see that extension of this one, it is quite well differentiating these two things. Okay, so our model were very close to the information which we got from the borewell. So this one was the one of the conclusion. Uh, then it further gave us the, what you say, further encourages that can we go for the three-dimensional visualization for that one. Now what we have for this one, so this field example is actually the based on the gravity and magnetic data sets together. This is a very large scale data. You can see that in y-axis we covered almost 50-kilometer region for that, and here we have a 25-kilometer for that. Here we have again 25-kilometer and 35-kilometer. So we collected magnetic data over here. Here we collected the gravity data over here. Now, important point is, can we make our model such that we should get some qualitative images apart from this image, uh, apart from this data. What we have in our hand is that we also collected some of the rock sample from the field, and we measure actual susceptibility and density value of that one to further utilize our ML based approaches to improve that one. So this one is the individual result of gravity, and this is the individual result of magnetic, uh, which we got from that one. You can see over that these two things are not following the exact pattern. For example, this whole our BIF zone you are seeing over here is belonging to this particular layer. Okay, BIF rock is only this one. But if you see that the high susceptibility also coming in this way. So to constrain that one, we you again further constrain with the rock sample, constraint based inversion we perform, and now you can see that how our data got improved, and also the improved model was showing over here. And though we got some of the scattered feature, but yeah, result were pretty much good. We obtained a very good quality based images, so that encourages us to go further for that one. Now uh, this one is the result of machine learning. Now I'll discuss the result of what we are trying to do with the deep learning. As I have mentioned to you that uh, different architecture what we have developed so far is to improve the subsurface imaging. We have a attention unit, and attention unit with the depth layer, and unit with the depth layer, and VED, which is our result. So this is the field data set which we provided to our network to see what different network will provide us the image. So this is our a true model. Also you can say the validation model. So this is the first C column you are seeing over here is the actually the unit. This is unit, and this is unit with depth, I think. And this is attention unit with depth, and this is VED which our student develop, and this is the traditional inversion which is we kept over here. Now important point you can see over here is that it is first we have taken the two layer problem. Let us say, take the two layer, only very simplest DC resistivity problem, two layer. The model was, first one in the model was, I think 20 or 15 ohm meter resistivity. Here we have a 100 ohm meter resistivity. Now unit architecture has given the model this has given the model pretty good model, but here it is some blurry third layer it is trying to produce. Unit with the depth layer you can see little bit providing it. But one of the important point of this unit also, that if you compare this with the traditional inversion, which I have I've tried to compare with that, it is still showing little better image of better image than this one. Now this one was the attention unit. Attention unit is providing little better image than unit, but attention unit with the depth layer is again not providing that one. That so much improved images you can see over that. Now, but if you compare with the variational encoder decoder network, you will notice that this is exactly, it is providing the same. If you are providing the 2D network data of this one, then predicted image was so satisfying, and it is very close to model. Now if you see that is if you compare our result with the three layer, first unit is 10 to the power 1.8 meter. This is further lower resistivity value, and this is further higher resistivity value. So we have taken three layer, and third layer resistivity is here, it is coming 0, and it is going up to that. Now again you come with the attention unit, you will notice that uh, it is almost failed to provide that one, but still it is trying to provide some of the better images. That one, uh, this is going up to here one image. This is the second layer, this is the third layer. So from the traditional inversion point of view, this image quality is not very image quality is better, but not very close to the true one. So again, though we have trained with the, I think 20,000 uh, data points, 20,000 images, still unit is not providing that image. But if you compare your attention unit network, you will notice that these images are still not providing that quality images. But the moment you will train with the VEG network, we notice that this image was uh, it has provided a very close to this network. So in our work, this VED network is working very effectively. A third, we have taken a different four layer problem. One is this greenish color, this is the sky blue, this one is the little darker one, and this is the reddish one is the fourth geologic unit. Now again, you will compare with the SEG net and SEG uh, uh, unit with the depth layer, and VNet with the depth layer. Then you will notice that it is still providing you the better images for this one, right? So it is providing you the better. So, but here one thing I would like to draw all of your attention, that uh, deep learning is something is very much dependent on what are the network uh, training data which you are going to provide to the network. So network should be trained very effectively. We are training our network in a very effective way. That is why we are getting our results very closer to this one. But if you will not train your network with the uh, traditionally, you might suffer with that. So overall, if you wanted to see the uh, concluding point of view, if you I would like to draw that one. So uh, in our research group, uh, what we have noticed that geophysical inversion geophysical inversion is one of the important and key point to obtain a subsurface image, but uh, this inversion is most of the time is not very sufficient to provide the most of the data sets. So to improve our image, one way forward is that over the study region, you try to utilize all the geological knowledge as well. For example, you try to utilize first multiple geophysical data set to improve your image, and also try to get the geological knowledge. For example, in our machine learning based architecture, what geological knowledge we try to incorporate into the machine learning? What are the number of geologic units presented over the study region, and what are the relation between these two physical properties are there. So similar, and we develop our architecture in such a way that they should obtain and provide very similar result of that one. Now second point is that uh, we transform our machine learning based approaches to not a spatial domain. We work with the parameter domain, such that there if there are only, we know that we have a borewell information, but depth information we have not included into that. So if someone will do this kind of work, that will be much better. And as a field example, I showed to you that if you jointly invert your two geophysical data sets along with the machine learning, your confidence will be on the subsurface model will be more as compared to what you obtain the individual network. And recently we tried some of the deep learning based results, and what we noticed that we compare our deep learning architecture with the very uh, uh, with the too much data sets. One was the SEG net, sorry, unit based, attention unit based, and ours variational encoder network. We noted that this is providing the best results so far. Uh, but one thing we noted down that this deep learning is highly dependent on the training set which we are going to provide to that one. So far we have developed our own training architecture to generate too much realistic geological model for that, and that we are providing to our unit and unit with depth layer or attention unit or attention video. So these results has provided very good result on that one. Now with that in knowledge, uh, what is the way forward of what is the way forward where we should move? So the one way forward, I would think is that over one study region, sorry, one way forward is that over one study region uh, we can utilize multiple data set, but not in a 2D framework. Still, the result which I have shown over here is the along one particular profile, not in a 2D. Yeah, gravity and magnetic data result were in a 3 dimension, but that were also from the gravity and magnetic. So, what if we have another data set? So, three or more data set, how we can incorporate, and is there any way? For example, one student asked, "What is the role of this? What is the role of this model regularization term?" So is there any way where we can utilize the structural orientation of the data? For example, geologically we know that in a particular region, uh, deep or a strike where the deep and strike is going in the subsurface are there. So mathematically can we incorporate those information using our model regularization term? Yeah, possibility is yes, but still we have to go further. Uh, like two data set, what will be the petrophysical relation which uh, can be measured using the different rock sample. So far now we have tried with the two different data set, but can we make a laboratory for that where three or more data set rock sample can be utilized and can be trained for that one. So there can be much more way to go ahead as far as computational efficiency is concerned. Yeah, computational task will require, but that is, I think doable. So with this kind of a model we should move forward. But for time being, what I would like to say that deep learning and machine learning are, we have not tried AI based. Deep learning is AI based approaches only, but these are the things which is uh, showing very promising result. uh, with this I can confidently say that we have utilized the field data as well. For that we got very good quality. That, so what I would say that it is showing some of the promising result of that, but still uh, we have to work very hard to train more and more for that one. So this way, I would say that machine learning and deep learning is helping us to improve the subsurface quality image. So with that, I'm going to conclude this session. If you have any questions, please let me know.
Dear participants, session is open for a question and answer. If you have any question, you can ask. Sir, I have a one query.
Yeah.
When we apply attention to a unit model, so what exact information we are trying to extracting using attention in unit model? Like unit model will give some information. What extra information we will get with the attention in unit model?
Okay. So this is the unit architecture which I have drawn over that. Is it visible to you?
Yes, sir, it's visible.
Yeah. So attention unit architecture we have drawn in this way. Okay. Now, if you see the attention unit, it has a slightly changed of that one. For example, here at certain locations we have kept the attention. We call this as a attention gate. Here what we do that we try to uh, keep as a, you can say, the check and balance of that, whether we are going in the right pathway or not. So that is why uh, uh, it is slightly different than this one, because we have kept here attention gate, we have kept here attention gate, here we have kept attention gate, here we have kept attention gate, to make sure that we are we are moving in the right path. And also that while doing the final convolution, uh, somewhere we have also utilized the skip connection. For example, from here to here, if you wanted to go, if it is not providing the better low loss function, then it can bypass and it can train using this pathway. So only difficulty is that uh, these two architecture is totally different than one over another. That is why it is providing the better image.
Sir, and the attention is applied only at the decoder part, not at the encoder part.
uh I think I won't be able to answer that one. I have to check with that. I think we have applied on the both part, but I'm not pretty sure, Deepak. I have to discuss with my student, but I think it is on the both part. And I'm not pretty sure.
Okay, sir.
I think we have encoder and decoder both part we are applying.
Okay, sir.
More detail, no, what if it is not clear, then more detail we can get the you can just search that Wilson et al 2012, this paper we just reported. So there more detailed way he has mentioned that, but right now I can't recall that whether the both way attention encoder decoder we are utilizing.
Sure, sir. Thank you. Participants, if you have any query, please.
I think most of them are tired hearing.
Thank you, sir. We'll conclude with a few points. Thank you, sir, for accepting your invitation for the speaker of a session. And I hope all the participants learn the latest trend in the interpretation of geophysics data using machine learning and deep learning. Thank you, sir, for sharing your valuable knowledge with all of us. Thank you very much, sir.
Okay, thank you, thank you.
Thank you, sir. Participants, the meeting, participants, the attendance link is shared in the chat box. Kindly fill the attendance.
So Deepak, can I leave now? No.
Yes, sir. Yes, sir. Thank you very much, sir. Thank
Okay.
you, sir.